This is the 16th video in a series of abstract linear algebra. And today we're going to start tying together some of the abstract notions that we've seen in the past with some more concrete notions that you might see at the very beginning of what I would call a standard linear algebra class. But armed with all of the construction and all of the structure that we've seen with our abstract constructions, these will go much easier or much quicker. Okay, so let's recall that if we have an m by n matrix A with entries in a field K, and if we have a vector x from Kn, then the product of A with x is a vector in Km. So this matrix times an n-dimensional vector is an m-dimensional vector. Let's also recall some of the arithmetic rules involving matrix vector multiplication. So we've got a distributive rule. A times x plus y is ax plus ay. And then we've got this rule that says that we can bring a scalar multiple out. So a times lambda x is lambda ax, where we're taking lambda to be a scalar. But notice these two properties right here mean that if we define a map T sub a from Kn to Km, which just multiplies a vector x by this matrix A, we get a linear transformation. So this is sometimes called the linear transformation associated with the matrix A. And then let's also recall we had this nice shorthand way of writing vector matrix multiplication down, and it went like this. So we've got A times x. So if A is defined column-wise, so A1 is the first column of A, A2 is the second column, all the way up to AN, which is the nth column. Then if we multiply that into the vector x, which has entries x1, x2 down to xn, we get the following linear combination of the columns. So we have x1 times a1 plus x2 times a2 all the way up to xn times an. So this is a nice shorthand way of writing down the product of a matrix and a vector that's not quite as messy as writing down maybe the matrix as an array. Okay, so let's do this a little bit more explicitly. So let's say we had this matrix 2, 3, minus 5, and then 1, minus 2, 4. And we multiply that into a vector. So notice we need a three-dimensional vector. So x1, x2, x3. And now using our standard strategy for matrix vector multiplication, I take this first row, swivel it to hit the entries of this vector, the overlaps get multiplied, and then they get added. So that means my top entry here is 2 times x1, plus 3 times x2 minus 5 times x3. And then likewise for my second entry, I swivel the second row into this column vector to give me x1 minus 2x2 plus 4x3. But let's notice I can factor that out as follows. I have x1 times the vector 2, 1, plus x2 times the vector 3 minus 2, plus x3 times the vector minus 5, 4. But those are exactly the columns of my original matrix. And that actually provides me some motivation for rewriting a system of equations as a matrix equation. And so let's do it with this example that we have on the board, and then we'll write it a little bit more generally over here. Okay, so let's say we've got the equation 2x1 plus 3x2 minus 5x3 equals, let's say, the number 7. And then we've got another equation, x1 minus 2x2 plus 4x3, let's say equal to 9, although I just chose those at semi-random. But notice we can turn this system of equations into a single vector equation. And that single vector equation would be 2x1 plus 3x2 minus 5x3, and then x1 minus 2x2 plus 4x3 equals the vector 7, 9. But now furthermore, by noticing what we did up here with our matrix vector multiplication, that is equivalent to the following matrix equation, which is 2, 3 minus 5 and then 1, minus 2, 4 into the vector x1, x2, x3 equals the vector 7, 9. So just to reiterate what we've done here, we've taken this system of equations, and via this matrix arithmetic that we've built, we found a way to write this system of equations as a single matrix equation. Okay, so let's get rid of this, and then we'll write down maybe a general happening of this over here, and then move on to some results. So here's a general version of what we had on the last board. So we've got this system of m equations with n unknowns. So the first equation is a11x1 plus a12x2 all the way up to a1nxn equals y1. And then the second one will be a21x1, a22x2, all the way up to a2nxn equals y2. And then down here, the mth equation will be am1x1, all the way up to amnxn equals ym. So again, we have m equations with n unknowns. But that's equivalent to the following matrix equation, where we have a matrix of coefficients. There are m by n. That's an m by n matrix, so there are m times n entries. Then here we have an n-dimensional vector made up of the unknowns, and an m-dimensional vector over here made up of the numbers, which are kind of the solutions to each of these equations. And then furthermore, if we wanted to introduce some shorthand, this could be the matrix A. We could wrap all of this up into the vector x and all of this up into the vector y. So we could write that as ax equals y. So that's a nice succinct way of collapsing this equation with m equations and n unknowns into a single matrix vector equation. Okay, so now we want to prove a result which actually follows immediately given the fact that we have a linear transformation by matrix multiplication. But that being said, we will prove it again just for practice. So let's suppose that A is an m by n matrix. Then the following two sets are subspaces in their parent vector spaces. So this first set is all y in km, such that ax equals y for some x in kn. So that's going to be a subset of km, and it's in fact a subspace, which is what we'll prove. And then the other one is all x and kn that get mapped to 0. So remember, this was the kernel of a linear transformation. When we're talking about a matrix, it's often called the null space of a matrix. Okay, so let's get to it. So we'll do this first one first. So how do we do this? Well, let's suppose that y1 and y2 are in that set. So in other words, they're in the set y of km such that ax equals y for some x in kn. Great. But now let's notice that that means there exists an x1 and an x2 in kn such that ax1 equals y1 and ax2 equals y2. Okay, that's just the entry fee to get into that set. But now we can see that y1 plus y2 is equal to ax1 plus ax2. But then using that distributive rule, we have ax1 plus x2. But the fact that we have y1 plus y2 is equal to a multiple of the matrix A, that tells us that y1 plus y2 is indeed in that set, which I won't rewrite. Okay, great. So I'll let you guys check the scalar multiple rule. So this set should also be closed under taking scalar multiple, but that should follow pretty easily by, again, the matrix arithmetic rules. Okay, so now let's prove this second result, that the null space is a subspace. So let's suppose that x1 and x2 are in this set right here, which I'll just go ahead and call the null space of A. But notice that means that A evaluated at x1 plus x2 is the same thing as ax1 plus ax2, but that's equal to 0 plus 0, which is equal to 0. So that tells us that x1 plus x2 is also in the null space of A, which is the name for this set right here. And then again, I'll let you guys check the scalar multiple rule as well. Okay, so now that we've got this taken care of, I'm going to actually define some terms based on these two subspaces. So let's maybe get rid of this proof and we'll put the definitions right here. So based on the fact that these two are subspaces of finite dimensional vector spaces, we know that they have a dimension. So since they have a dimension, and these are kind of really important subspaces, we should give that dimension a name. And so this first one is called the rank. So in other words, the rank of the matrix A is the dimension of its image. In other words, the dimension of the subset of all y in Km such that y is equal to ax for some x in Kn. Next, the nullity of A is the dimension of its null space. In other words, the dimension of its kernel or the dimension of the subspace of all x and Kn such that ax equals 0. So this rank and nullity are really important ideas. So we'll refer to the dimension of these subspaces enough that we should really give them names. And so that's why we've done this. Okay, so let's move on and prove a couple more results. So next we're going to prove a really nice way of describing the spanning set for the image of a matrix, or really the image of a linear transformation that's defined as a matrix. So in particular, we'll show that the image of a matrix A is just the span of the columns of A. That's also known as the column space of A, and is often denoted by just the COLA. Okay, so let's maybe see how this goes. So let's suppose that y is in the image of A. Okay, but that means that y equals A times x for some x in Kn. So that's what it means to be in the image of A. But now that means that y is equal to, let's recall that we can expand A out in terms of its columns. It has n columns, A1, A2, all the way up to AN, times x1 down to xn, where we've expanded x, the vector, in terms of its entries. But now let's recall by matrix vector multiplication, this is equal to x1a1 plus x2a2 plus all the way up to xnan, where a1, a2 up to an are the columns of A, but the x1, x2 up to xn are really just numbers. They are the entries of the vector x. But since these are just numbers, that gives us a linear combination of the columns of A, but that's exactly what it means to be in the span of the columns of A. In this case, A1 up to AN. Okay, nice. But now notice that that tells us that the image of A is a subset of the span of the columns of A. And so, of course, to show that they're equal, we need to prove the other containment as well. But that's actually just a straightforward reversal of this. So let's see how it goes. So let's suppose maybe I'll call it V is in the span of the columns of A. So A1 up to AN. But notice that means that V is equal to C1 times A1 all the way up to Cn times AN. It's a linear combination of the columns. That's what it means to be in the span. But now let's notice that that means that V is equal to the matrix A times the vector C1 down to Cn. Okay, but that is exactly equal to A times C, where C is this vector C1 down to Cn, which is in Kn. But that's exactly what we need for V to be in the image of A. But that proves the other containment. In other words, now we have shown that the span of the columns is contained in the image, but then if we have both containments, we have the equality, and that's exactly what we wanted to show. Now we'll prove a result about the size of the nullity of a matrix. So let's suppose that A is an m by n matrix with entries in K again, but now we also want to tack on the rule that n is bigger than m. Then that means the nullity of A is at least n minus m. Okay, and here we're going to use a result of a previous theorem about abstract linear transformations that's been applied to our setup. So in particular, let's consider the following linear transformation, TA, which goes from Kn to Km, defined just by multiplication by the matrix A. So in other words, TA evaluated at X is A times X. Okay, so by previous, so I think it was like 2 or 3 videos ago, we know that the dimension of the image of TA plus the dimension of the kernel of TA is equal to n. So I don't think we called this the rank-nullity theorem then, but when it's applied to matrices, it's called the rank-nullity theorem. Okay, but notice that the dimension of the image of TA, that's the same thing as the dimension of the image of A, because that's how this linear transformation is defined. So this is the rank of A, but then the dimension of the kernel of this linear transformation is just the dimension of the null space of the matrix A by how we defined this linear transformation. So we have the rank of A plus the nullity of A is equal to n. And I think this is the proper statement for the rank-nullity theorem. Okay, but now we can say that the nullity of A is equal to n minus the rank of A. But that is most definitely bigger than or equal to n minus m. And why is that? That's because the rank of A will be less than or equal to m. How do we know it's less than or equal to m? That's because the image of TA, or the image of A, if you will, is a subspace of the vector space Km. So that means its largest possible dimension would be the whole vector space, which would be m. Okay, so that proves this proposition. And we'll finish this video off by starting to prove a really important theorem that ties lots of different ideas together. So let's get to that. So here's the big theorem that we'll finish this video off with, and this theorem will be added to throughout the remainder of this series. So let's suppose that A is a square matrix of size n. So it's n by n. Recall that we denote that as being an mn k. So we've got entries in a field k. Then the following 6 statements are equivalent. So first is the linear system ax equals y has at least one solution for all y in Kn. Notice that essentially just says that it is an onto function or a surjective function as a linear transformation. The second statement is that the columns of A span Kn. The third is that the null space is trivial. In other words, if ax equals 0, then x equals 0. The kernel is trivial, if you will, as well. The fourth is that the columns of A are linearly independent. The fifth is that ax equals y has exactly one solution. And the sixth is that the columns of A are a basis for Kn. Okay, so we're going to prove this in like a round robin kind of setup. So we'll prove 1 implies 2, implies 3, implies 4, implies 5, implies 6. That implies 1. And so that means they'll all be equivalent. So that being said, let's start with 1 implies 2. So in other words, we're supposing that this linear system has at least one solution for all y in Kn. So let's suppose that y is in Kn. That means that there exists an x. I'll go ahead and call it x1 down to xn in Kn, such that ax equals y. So again, that x is our solution. But now let's note that that allows us to write y as, well, I'll write it as ax again, but then using like rules for vector matrix multiplication, that's equal to x1 a1 plus x2 a2 plus all the way up to xn an, where using our notation before, the x upper 1, upper 2, so on and so forth are the columns of A. So this is definitely an element of the span of the columns of A, this A upper 1 up to A upper n. But that's exactly what we wanted to do, show that the columns of A span Kn, and that's what we've done. We took an arbitrary element from Kn right here, and we showed that it was in the span of the columns. So we're finished proving 1 implies 2. So next, let's do that 2 implies 3. So in other words, we are assuming that the columns span Kn, and then we'll show that the null space is trivial. So let's go ahead and suppose that X is in Kn such that Ax equals 0, but X is not equal to 0. So just to be really clear here, we're working towards a contradiction. So let's put that in here. We're working by way of contradiction. So that means we can write X expanded out as X1 down to Xn, where Xi, for instance, is non-zero. That's what it means to have a non-zero vector. At least one of the entries is non-zero. Okay, but now let's expand this out in terms of columns again. That allows us to write X1, A1 plus all the way up to Xi, AI plus all the way up to Xn, An equals the 0 vector. But given that this Xi is non-zero, that allows us to solve for the AI. And so that means we can write this A upper I as, let's see, 1 over Xi. Let's maybe put a minus sign out front. And then we'll have X1 A1 plus all the way up to, I'll put Xi AI here with a hat over it to say that we are removing that from the sum. And then all the way up to Xn An. But notice that's an element of the span of A1 up to AI, removing it up to An. But let's recall that we assumed that Kn was equal to the span of A1 up to An. That was what number 2 was, the columns span Kn. But since AI can be written in terms of the other ones, that means we can remove it from this spanning set. So we have the span of A upper 1 up to A upper I removed up to A upper N. But that's a problem because that tells us that the dimension of Kn is strictly less than n because it's spanned by less than n vectors. So like I said, that is a contradiction. So what fact have we contradicted? Well, we contradicted this assumption right here where we assumed that x was not equal to 0. So that means that x must in fact be equal to 0. Which is exactly what we wanted for this. We wanted to show that the only solution to this equation was the trivial solution. So that finishes off 2 implies 3. And now let's move on to 3 implies 4. So I think that's a bit shorter so we can fit it in down here. So let's see. We want to assume that the only solution to this equation is the trivial solution and prove that the columns of A are linearly independent. So let's try to set up a linear dependence relation. So let's suppose that we have x1 up to xn in K such that x1 a upper 1 plus all the way up to xn a upper n equals 0. And that's 0 like the 0 vector in Kn. But we can rewrite this sum of vectors as a matrix vector equation. So that means that a times x is equal to 0, where x is just the vector built out of all of these x's. But then by our assumption, which is number 3, we know that that means that x is the 0 vector, but that means that xi equals 0 for all I between 1 and n. But let's see where we started and where we ended. So we assumed that we had a solution to this equation, and we showed that the only solution was the trivial solution, but that's exactly the condition for these columns to be linearly independent. So that finishes the proof of 3 implies 4. Okay, so let's clean this up and then we'll go to 4 implies 5. So now we're ready to do 4 implies 5. So we know the columns of A are linearly independent. That means we need to show that ax equals y has exactly one solution. So let's recall that we have a1 up to an linearly independent Another thing we notice is that these are n vectors from Kn. And so that's a maximally linearly independent set, but that means it's a basis. But if it's a basis, then that means it spans Kn. So we have the span of A1 up to An equals Kn. So we proved why these kind of arguments work several videos ago. Okay, but if the span of A1 to An is Kn, then that means for all y in Kn, we have a combination of xi and k such that x1, a1, all the way up to xn, kan is equal to y. But again, we're going to do kind of the same thing we've been doing and rewrite this vector equation or vector sum equation into a matrix vector equation. So that means that A times x equals y, and we found a solution to ax equals y. It's these numbers right here that go along with the spanning. Okay, so that tells us that we have at least one solution. Now we want to show that there is exactly one solution. So let's suppose that w and x are in Kn such that ax equals y equals aw. Great. So just to reiterate, up here we showed that there must be a solution. Now we're going to show that that solution is unique. But notice the fifth statement is exactly that. Okay, but now if ax equals y and y is equal to aw, that tells me that ax minus w equals 0. And now we're going to expand this back in terms of sums of columns. So notice that that means that x1 minus w1 times the first column all the way up to xn minus wn times the nth column equals the 0 vector. So notice we're like skirting our way back and forth with several of the same facts. And a lot of this looks pretty similar, but we have to do that because these things are so interconnected. And really, we're just going from a single statement to the next statement without using any of the previous statements. Okay, so anyway, now we know that the columns are linearly independent. That was our assumption. But we've got something that looks like a linear dependence relation. That means that it can only be solved where the coefficients equal 0. So that means that xi minus wi equals 0 for all I, but that means that xi equals wi, which means x equals w as a vector. So that means if we had two solutions, then in fact those two solutions were the same. And that finishes the proof of 4 implies 5, and we're ready for 5 implies 6. So now we're ready to prove 5 implies 6. And so that's the existence of this unique solution implies that the columns of A are a basis. So notice we've flirted with the columns of A being a basis before, but now we're just assuming number 5. Okay, so let's start by showing spanning. So let's suppose that y is in Kn, and then we can find an x in Kn such that ax equals y. And so that's by this right here that it has exactly one solution. Here we're using the fact that it has at least one solution. Okay, but now again, we're going to expand this as a sum of the columns, and we'll write y as x1, a1, all the way up to xn, an, which, like I said, is in the span of the columns of A. Great, but that tells us that Kn is a subspace of the span of the columns of A. But the span of the columns of A is clearly a subspace of Kn because it's a span of vectors in Kn. But that means that the span has to be equal to Kn. Okay, now, well, we can use a dimension argument again to say that since we've got exactly n vectors here and an n-dimensional vector space, then they also have to be linearly independent. But let's do just a little bit more work for practice. And so keeping that in mind, well, we showed spanning, and in order to have a basis, you need spanning and linear independence. So let's suppose that maybe we'll call it U1, A upper 1, all the way up to UN, A upper N equals 0. So a would-be linear dependence relation. So we want to show that all of the U's are 0, but that shouldn't be too hard. Notice this implies that A times the vector U, which is made up of the entries U1 up to UN, is equal to the 0 vector. But notice the 0 vector is the same thing as A times the 0 vector. But now let's recall that every equation like this has exactly one solution. But we've exhibited two would-be solutions, U and 0, but the fact that you can only have one solution means that U is equal to 0. But if U is equal to 0, that means UI is equal to 0 for all I, which is exactly what we needed to show for linear independence. Okay, so I guess that leaves us one more thing to do, and that is 6 implies 1, and that will finish this loop. And so if the columns of A are a basis for Kn, we need to prove that this linear system has at least one solution. So that shouldn't be too hard to do. So let's suppose that Y is in Kn, but since the columns form a basis, that means the columns span Kn. So that means that Y equals x1 A upper 1 plus xn A upper n. We found again, that's by the spanning, but that's equal to A times X in terms of our matrix vector multiplication. But that's our solution. Okay, so that finishes the proof of 6 implies 1, which is exactly what we needed to do to finish the proof of this whole theorem. So later, we'll tie this into the invertibility of a matrix, but we're not quite ready for that yet. Okay, so I'll leave you guys with some warm-up problems. So here I've got 2 warm-up problems. So this first one really could have been given in the last video, but we did a lot of results in this video and not really a lot of brand new information. So there aren't really a lot of warm-up problems based around this material. So anyway, the first one is to list all invertible matrices in M2F2. So let's recall that those are 2 by 2 matrices where the entries are in the integers modulo 2 viewed as a field. Okay, and then I'd like to point out that this is exactly the 2-dimensional general linear group on F2, which is denoted by GLF2. What I mean is that the set of all of these invertible matrices forms a group. Recall we talked about groups a while ago, and that group is called GLF2. Okay, so the second one has to do with this theorem right here. And that is express this x1 plus 3x2 equals 9 and 2x1 minus x2 equals 11 as a single matrix equation, and then argue why it has a unique solution without solving it. So just write down the matrix equation and then use some results that are maybe over here to say why it has a unique solution, but do not find that solution. Okay, that's a good place to stop.